Hello, Calculus fans. Somebody asked this on the discussion board. It's an old exam question. They didn't actually ask this question. They asked whether their answer was acceptable, which I will answer here, but it brings up a bigger issue, which is how do we deal with irreducible quadratics? I give a method in class of separating them, so you don't have to use trig sub, but trig sub also works. The answers might look a little different in the end, and I'll talk about that at the end of this, but I just wanted to compare. I always say I like to do it this way, but maybe I'm wrong. So here's what we're going to do. We're going to do a little test, and then you can decide which one is better. I'll solve it both ways. Hope this is interesting. So first off, in this case, it looks like a partial fractions problem. It doesn't look like a trig sub problem because there's no square root. But there's this darn middle term, this 6x. But we've learned how to handle that. So first, what you're going to try to do is factor. And you're going to spend however long you want to take, but I suggested only 10 seconds to try to think up two numbers that multiply together to give you 13. Now, right away, I'm starting to think it's not going to be whole numbers because the only whole number factors are 1 and 13, and none of those add up to 6. So I already think they don't factor. So as I said in class, you try to factor for 10 seconds. If you're unable to factor it, then you try to complete the square. That's the strategy no matter what, whether you're going to do either one of these. And we talked about how if you accidentally didn't realize you couldn't factor it, you'll find that out in just a moment. So I was unable to factor it, I'm going to complete the square. The way we complete the square is I always like to put a 1 in front of x if you're in my class. There's a longer discussion we could have, but I'm trying to be practical here. So the technique is to ask yourself, and that's a separate video, half the middle squared, so you need a 9 there. That makes a perfect square. But you have to deal with the consequences. There wasn't a 9 there, there was a 13 there. So if I'm going to add in a 9, I need to also subtract a 9. That's a little maneuver. And you don't want to move forward unless you're certain it's right. Now, I mentioned about knowing that you're factoring. The moment you see that this is a plus, confirms that you couldn't factor. If it's a minus, it actually means you could factor. There's another way to see if it's irreducible is to try to solve when is this equal to 0 with the quadratic formula. And if you get a negative under the radical, then it's irreducible. There's a lot more to say. But anyways, at this point, you now have two options, and this is where I'm going to step into, and I'm going to try to give it as fair a comparison as possible. So I would say if I was going to do trig sub, I probably would do it directly from this step. It's probably the fastest. And I might take another step here. So we're going to start both these problems, and then we're going to do a comparison. Okay, so on the left, we're going to have the technique I like to use, which is to separate. Now, in order to separate, I typically advise students to do the following substitution. This just cleans it up so it looks more familiar. The only note is you have to realize that x is equal to t minus 3. So if that really bugs you, then maybe you'll have to wait for the second method. But this really isn't that bad. T squared plus 4 dt. And then my advice is to separate it. It is important to do that substitution to make the separation easier to handle. Minus the integral of 3. If you're paying attention in class, both of those are integrals we can quote. One of them you may or may not recognize. This is arctangent. Hopefully you recognize this one. T over 2 plus c. And this one, so this, again, another step here that if we have to stop, this does slow this technique down. If you don't know what this one is, you would have to do u equals. I did include this in our lecture and discussion. So this can be done in one step if you want. But let's for now just pretend we don't know what it is. You would have to do this on that. In which case you get the integral of 1/2 1 over u du. But the truth is, I am perfectly happy with you just saying 1/2 the log of t squared plus 4. But I didn't want to hide the fact that if you've forgotten that one or it wasn't on your sheet, you would have had to do this substitution. You would have gotten the log of u 1/2. You might be wondering, why didn't I put absolute values, which is a good question. I wouldn't mark someone down for putting them, but t squared plus 4 is positive, so it's unneeded. There's our answer, but we're not quite done. You would have to return to x, so log, this would be x plus 3 squared plus 4. It just depends on how pretty we want to make it. I could return all the way back to the original if I wanted. 2 plus c. Okay, so there's our first option, separate. What I like is since we do encounter irreducible quadratics in a few settings, it's kind of nice to just have a strategy of split it up, and both things are things we know. Okay. Next up, what if we do trig sub? So if I was trying to think of someone who's trying to argue with me about preferred method, you could argue that you don't need to do this if you're doing trig sub. So I'm going to try to just go do directly and do x plus 3. A lot of people, when they do trig sub, do this anyways, which would add a couple steps, but you don't have to. So the trig sub would be 2 tangent of theta, because that's a plus and that's a 4. The derivative would be 2 secant squared of theta d theta. You'd have to solve for x, so x would be 2 tangent of theta minus 3. And you would need to simplify. And you can do that if I was trying to be as fast as possible, I might do that in the margins. So when I plug this in, the denominator is going to become 4, because that's going to be squared. Tangent squared of theta plus 4. So it's going to be 4 tangent squared of theta plus 1. So it's going to be 4 secant squared of theta. Okay, so let's do all the substitution. The top's going to be 2 tangent of theta minus 3. The bottom is going to become 4 secant squared of theta. The derivative is 2 secant squared of theta d theta. It appears there's some cancellation, quite a bit, here. It's going to become a 2. So I have 1/2 the integral of 2 tangent of theta minus 3 d theta. And then we're going to integrate. You'll have to remember that tangent is log of secant. You'd have to look that up on the table. And you'd have to remember that this is 3, or not remember, just 3 theta. And then you do the little triangle trick. So let's review that. Scroll this up a little bit. Let me zoom out. Sometimes when I repost these videos, my face blocks the right-hand corner. Eventually I'll get better at that. But so we have opposite over adjacent. That's tangent. I don't usually rewrite it, but maybe you would take a moment and do this. And you would solve for the other side, which is going to be the square root of this squared plus that squared. So square root of x plus 3. There's always a square root there, even if there isn't one up here. Okay. And so then we have 1/2 to the log of secant. And secant would be hypotenuse over adjacent. This is going to be the square root. Similarly, that's positive because it's the positive square root of something. So at this moment, I don't need the absolute values. Minus 3 arctangent of x plus 3 over 2 plus c. So if we distribute the 1/2, we get the log of the square root. Maybe let's clean this up. X squared plus 6x plus 13, just because I know that's what we started with. This is 2. And then we have minus 3/2 arctangent of x plus 3 over 2 plus c. So that's correct. Full points. That's correct. And honestly, years ago when I did this, I didn't really do a comparison. I just thought most people preferred if they could do it in 2 steps and reduce it to integrals they know. I thought students would prefer this. But I have noticed in recent years more people do trig sub. They're both perfectly fine with me. And those are both acceptable answers. But a natural question is, what are you saying that these are both acceptable answers? Those don't look the same. So we'll finish this video with a little discussion about, in fact, I think those are not the same. What? So let's talk about that a little bit. Let's take this one and write, so the few log rules. Log of A over B is the log of A minus the log of B. These are the two most important log rules by far. And the most important one is this second one, because this is what you use every time you're solving an exponential equation. So in this case, we have a 1/2 out in front, so you can write it equivalently as a square root. So the first answer I gave could have been written as the square root of this thing. And now the answers look similar, except of this 2. So you say, well, what about that 2? Well, this can be written as the log of the square root of x squared plus 6x plus 13 minus the log of 2. And the truth is, those are not the same. So did we mess up? No, the goal was to find a general antiderivative. If you take this and write it, my answer using the separation technique is this, and then we have this other thing that's the same. Arctangent of x plus 3 over 2 plus c. There's my answer. And here's this other person's answer. The log of the square root of x squared plus xx. And I'm just going to rearrange it a little bit. So I'm going to copy so it looks exactly the same. And there's this negative log of 2 plus c. And the truth is, the difference between our answers is a constant. But that means they both express the same general antiderivative. What it means is these constants are different. So if I labeled this one d and this one c, d would always be negative log of 2 plus c. So for example, if c was 10, then d would be negative log of 2 plus 10. If you look at it for a given initial condition, you would have the exact same answer. Sometimes you can think of it as the constant is absorbed. So you don't necessarily have to have this function the same as this function in order to have the correct answer. But they need to be, if you were to graph them both, they need to be shifted versions of each other. They should look like the same graph. If it's shifted up and down, it's still correct. Okay, hope that's interesting and helpful.